Okay, I think we're live. Good morning, afternoon. Good afternoon, gentle people. Today is going to be a very basic understanding of how programming works. If you've never coded anything in your life, this is going to be talking about variables, mutability. What else are we talking about? Declaring constants, shadowing, data types, comments. How do you put that in your editor? So many basic things. So if you don't really need a basic rundown on how Rust works and you want to go into more of the complex ownership types, that will be next chapter. Okay. Today we're going to really just dive into those fundamentals, and it's good to get your feet wet with these. And I think it's just going to be a whole reading day. There's going to be no projects. Okay. And most of the code does run in the book. So you'll see me running some of the code, but it'll be within the book. You'll see. You'll understand. All right. Let's jump right into it. So today we're talking about variables and mutability. As mentioned in the storing values with variables section, by default variables are immutable. This is one of the many nudges that Rust gives you to write your code in a way that takes advantage of the safety and easy currency that Rust offers. However, you still have the option to make your variables mutable. Let's explore how and why Rust encourages you to favor immutability and why sometimes you might want to opt out. When a variable is immutable, once a value is bound to a name, you can't change that value. To illustrate this, generate a new project called variables in your project directory by cargo new variables. Then in your new variables directory, open source/main rs and replace its code with the following code. Now, you can follow along. I guess, you know what? Let's do what they say. Let's go back to our projects. It's always good to just do the projects as well while we're learning. Come on, get in there. It's too little. Alright, we're back in our projects folder. Last week we did, not last week, yesterday, we did our guessing game. And it's super fun. I don't think we played it as much, but play it at on your own time. I've already done one of these before, so it's super fun. Okay, what does it say? It said to create a new project's cargo new variables. So cargo new, and we're creating variables within our project folder, and then we're going to change directory into our variables project. Well, does that. Okay, change directory, variables. Now we're in it. And now you can see our directory. Okay, I mean a project. Okay, we're in our main RS. And I'm just going to do a little cargo build because it's always good to double check, see if it will build into a cargo run. And hello world, and it compiles perfectly. Perfect. Alright. Alright, so then in your new variables project, replace its code with the following code, which won't compile just yet. So we're doing a let x, and we're binding it to this 5. Then we're doing a print line of what the value of x is, and then this is a placeholder that we learned in yesterday's video, which it should show the number 5. Then we have x equals 6. We're also shadowing because we're using the same variable that we bound 5 to, now we're binding x to 6. So then we're going to print the value of x is x, which should be 6. And let's see what it does. I'm just going to copy, actually, let's just copy that code. Just copying that code because it's so much to write all that. All right, and then we're going to do another cargo run. And let's look at this. What does it say? All right. Okay, so you should receive an error message regarding immutability error as shown in the output. So we have let x equal 5. First assignment is to x, print line, and then the value of x is 5. But we're reassigning that same variable that we just assigned 5 to 6. So we can't reassign it. You know why? Because we didn't put mute, which by default, because it's immutable, we have to put the mute variable, before the variable. This example shows how the compiler helped you find errors in your programs. Compiler errors can be frustrating, but really they only mean that your program isn't safely doing what you want it to do yet. They do not mean that you're not a good programmer. Far from it. Experienced rustaceans still get compiler errors. I get them all the time. You received the error message cannot assign twice to immutable variable x because you try to assign a second variable to the mutable x variable instead of putting mute after the let. Okay, so it should be let mute x equal 5, and then when you reassigned it as shadowing that same variable, you will be able to do that because you have mutable now. It's important that we get compile time errors when we attempt to change a value that's designated as immutable, because this very situation can lead to bugs. If one part of your code operates on the assumption that a value will never change and another part of the code changes that value, it's possible that the first part of the code won't do what it's designed to do. There's these safety measures in place for you. Then cause of this kind of bug can be difficult to track down after the fact, especially when the second piece of code changes the value only sometimes. The Rust compiler guarantees that when you state that the value won't change, it really won't change. So you don't have to keep track of it yourself. Your code is thus easier to reason through. You can find where your bugs are based on your compiler errors, essentially what it's saying. But mutability can be very useful and can make code more convenient to write. Although variables are immutable by default, you can make them mutable by adding mute in front of the variable name, as we did in chapter 2, if you remember from last video. Adding mute also conveys intent to future readers of the code by indicating that other parts of the code will be changing this variable's value. All right, so you can see here, now we're going to copy this. We can run it here, but I changed my mind. I'm going to run it here. Oops. We're in our variables folder. Don't be switching back and forth. We're going to do cargo run. And when we run this program, we get this. Any day now. All right. We get this. The value of x is 5. Then we change it to the value of x is 6. We're allowed to change the value bound from x from 5 to 6 when mute is used. Ultimately, deciding whether to use mutability or not is up to you and depends on what you think is clearest in this particular situation. Yay! You know what? It's always my camera that, you know what, I'm just gonna leave it like how it is because I can't read. It's like behind my camera for some reason. Alright. Declaring constants. Like immutable variables, constants are values that are bound to the name and are not allowed to change. But there are a few differences between constants and variables. First, you aren't allowed to use mute with constants. Constants aren't just immutable by default, they're always immutable. You declare constants using the const keyword instead of the let keyword, and the type of value must be annotated. We'll cover types and type annotations in the next section in data types, so don't worry about the details right now, just know that you always annotate the type. Constants can be declared in any scope, including the global scope, which makes them useful for values that many parts of the code need to know about. Fun. The last difference is that constants may be set only to a constant expression, not the result of a value that could be computed at runtime. I don't know what that means. That was a weird sentence. I'm going to read it again. The last difference is that constants may be set only to a constant expression, not the result of a value that could only be computed at runtime. Hopefully they clarify what that means. Here's an example of a constant declaration. So we have our constant, that's what makes it a constant, 3 hours in seconds, and then we're using the type, remember, unsigned 32-bit equals 60 times 60 times 3. So we're doing some math, and we're binding it to that variable 3 hours and seconds. Okay. Now the constant type is 3 hours and seconds, and the value is set to the result of multiplying 60, the number of seconds in a minute, by 60, the number of minutes in an hour, by 3, the number of hours which we want to count this program. Okay. I hope that makes sense. Rust naming convention for constants is to use all uppercase with underscores between words. Okay. The compiler is able to evaluate a limited set of operations at compile time, which lets us choose to write out this value in a way that's easier to understand and verify, rather than setting this constant to the value of 10,800. All right. See the Rust reference section on constant evaluation for more information on the operations and what operations can be used when declaring constants. Constants are valid for the entire time the program runs, with the scope in which they are declared. Okay, so usually when you declare a constant, what I do is it's going to be at the top of my program, because it's going to be declared, it's going to be used within the program the whole time. Like it says, it runs the whole time. So that's pretty much the only time you're going to use a constant when you know you're going to use it for your whole program. You know what I mean? Or it's going to be used multiple times through your program. Okay, this property makes constants useful for values in your application domain that multiple parts of the program might need to know, such as a maximum number of points a player of a game is allowed to earn, or the speed of it. Naming hard-coded values used throughout your program as constants is useful for conveying the meaning of the value to future maintainers of the code. It also helps to have only one place in your code where you would need to change if its hard-coded value needed to be updated in the future. That's why I put it at the top. It's just easier for when you do need to change that hard-coded value, is right at the beginning of your program. All right, shadowing. We did a little bit of this in the last game that we created, our guessing game, and now we're going to go over it again. And we kind of did it not so long ago. Okay, as you saw in the guessing game tutorial in chapter 2, you can declare a new variable with the same name as the previous variable, as we did actually right here, x and x. Rustaceans say that the first variable is shadowed by the second, which means that the second variable is what the compiler will see when you use the name of the variable. In effect, the second variable overshadows the first, taking any uses of variable name to itself until either it... What? In effect, the second variable overshadows the first, taking any uses of the variable name to itself until either itself is shadowed or the scope ends. Okay. We can shadow a variable by using the same variable's name and repeating the use of the let keyword as follows. Okay, scope. I don't think we've been through this as I don't think we've talked about scope. Scope is your curly braces. These little curly braces when you're creating a function. Once it has ended, let's say I'm using these curly braces as my scope. This whole function should be maintained within these two curly braces right here. Once it is out of that scope, that's it. It's done. Whatever the function has run should be complete. That's why a lot of times it's going to talk about scope in the later chapters. The scope is those curly braces essentially for each function, or let's say like you have a scope within a variable. That's your scope, those curly braces. This program first binds x to the value of 5, then it creates a new variable x by repeating let x equal, taking the original value and adding 1 so that the value of x is 6. Then within the inner scope, this is the outer scope, which I was showing before. Now we have an inner scope, which is a nested scope. Just another way of saying it, which is right here, these curly brackets. And it's difficult when you are first starting to understand your code, where these brackets are encompassing, and sometimes it's easier to see like the indentation. So usually if something is within it, it will be indented. So you see that this one's all the way over here, this one's indented over here. It's just easier. All right. Where was I? Okay. So I'm gonna read this again. This program first binds x to the value of 5, then it creates a new variable x by repeating let x equal, taking the original value and then adding 1, so that the value of x is 6. Then within an inner scope created within the curly brackets, the third let statement also shadows x and creates a new variable, multiplying the previous value by 2 and then give x a value of 12. When that scope is over, the inner shadowing ends and x returns to being 6. Okay, interesting. So let x equal 5, and then we have 5, which is now x, equaling, which this would be 5. So this would turn into 5 plus 1, which would be 6, which is what's saying right here. So now x is 6. Then we have this inner scope, let x equal x times 2. So now, because it's not 5 anymore, so get this out of your brain. Now it is 6. So now we're going to let x, which is now binded to 6, equal 6 times 2, which will equal 12. This is only valid within this scope. So when you print line this x, it's going to show 12. Now, in this scope, do you see that? This is a different scope. This is your inner scope and this is your outer scope. Within your outer scope, when you print line the value of x is, it's going to still be 6. And that's what you can see right here. Cargo run And then you see the value of x in the inner scope is 12, and the value of x in the outer scope is 6. I hope that makes sense. If you need more explanation, you can always ChatGPT it. ChatGPT is great. Alright. Shadowing is different from marking a variable as mute, because we'll get a compile time error if we accidentally try to reassign this value without using the let keyword. By using let, we can perform a few transformations on the value, but have the variable be immutable after those transformations have completed. So you need to use your lets, okay? The difference between mute and shadowing is that because we're effectively creating a new variable when we use the let keyword again, we can change the type of the value but reuse the same name. For example, say our program asks a user to show how many spaces they want between some text by putting space characters. And then we want to show the score. Oh, we want to store that input as a number. So here we have our little variable, let spaces equals spaces dot len. Now the first spaces variable is a string type, and the second spaces variable is a number type. Shadowing thus spares us from having to come up with different names. Woo. Different names such as spaces underscore string, spaces underscore num. Instead, we can reuse the simpler spaces name. However, if we try to use mute for this, as shown here, we'll get a compiler error. What? The error says we're not allowed to mutate the variable's type. Okay. Now we have explored how variables work, let's look at more data types. I feel like this explanation could have gone a little bit more because I would say use this shadowing sparingly. Sometimes it can get a little bit confusing, and I feel like they didn't really do a good job of telling us what the reason why we can't use mute. So it says the first is spaces, second spaces variable type. I guess because there are two different types, having a mutable variable, it would have to be the same type. I'm pretty sure, and this is me just interpreting whatever we're reading, I'm pretty sure the shadowing has to do with actually mutating the type as well. So you can shadow the same variable name and then have it as a different type. I'm thinking that's what they're trying to say. But I would say use this sparingly, unless you really need to use this, just use a different name. It's okay. It's alright. It's alright. Okay. Alright, we're on to data types. Let's see. We got a couple different data types, and we're going to be talking about every value in Rust has a certain data type, okay, which tells Rust what kind of data is being specified so that it knows how to work with that data. I don't think we really need this right now, so I'm just going to put this away, and let's just put this full screen, okay, because this helps me read. Alright. We'll look at two data type subsets, which is scalar or scalar. Scalar. I'm just going to say scalar and compound. Keep in mind that Rust is statically typed language, which means that it must know the types of all of the variables at compile time. So it's better to actually type your variables, even though you're going to see later on that sometimes you don't need to type it and it will assume which variable that you're using, but I think it's good practice to know. Typing, this is what it means by typing. Do you see this? So you're binding this guess variable to this string 42. and whatever is behind it. But this colon U32 bit, that's your types. Okay. Okay. The compiler can usually infer what type we want to use based on the value and how we use it. In cases where many types are possible, such as when we converted a string to a numeric type using parse. In the comparing the guess to secret number section in chapter 2, we must add a type annotation like this. So, very good example of what we did last time is we had a variable that was a string, but we need to change it to integer, and using the type, like typing system, we put that U32 bit. So it essentially is showing you right here, this was a string, but using parse, we changed that type to an integer. If we don't add that colon U32 bit type annotation shown in the preceding code, Rust will display the following error, which means that compiler needs more information from us to know which type we want to use. Okay. Yeah, see. Let guess type. So it's telling us to type it because it's confused. It's panicking as to, like, what is this? Could not compile, no type annotations. It's good to read your errors just to get familiar with how it's yelling at you. Okay, scalar types. A scalar type represents a single value. Rust has 4 primary scalar types: integers, floating point numbers, booleans, and characters. You may recognize these from programming languages. Let's jump into how they work in Rust. Integers. An integer is a number with a fractional component. We use one integer type in chapter 2, the U32, which means unsigned 32-bit integer type. And this type declaration indicates that the value is associated with should be an unsigned integer. Okay, signed integers start with an I instead of a U. The unsigned is U, integer is I. If you don't know what an unsigned integer is, actually, are they going to be telling us about that? Oh, yeah, they will. Okay, stay tuned. This is the integer size. Usually, if it's a smaller integer, I don't know, I think this goes up to, bro, how do I know? 2 to the power of 8, what is that? Don't ask me. I'm not really good with numbers. You can look up a little chart and see where your integers will lie. There's a range for how much capacity it will take to hold that specific integer, and you will use it based on that. But I think it's usually we use an I32 or a U32. If it's a bigger number, maybe in the millions, I would use a U64 bit or an I64. It's just easier. If you know that you only want a limited amount of space and you only want to use that much capacity, go for a smaller integer then, or specify which integer would be in that range. Each variant can be either signed or unsigned and has an explicit size. Signed and unsigned refer to whether it's possible for numbers to be negative. In other words, whether the number needs to have a sign with it, signed, or whether it will only ever be positive and can therefore be represented without a sign, unsigned. So think of a plus or a minus that would be signed, that would be an integer. Unsigned is all positive. You don't need anything in front of it. It's never going to be a negative. It's like writing numbers on paper. When the sign matters, a number is shown with a plus sign or a minus sign. However, when it's safe to assume that the number is positive, it's shown with no sign. Signed numbers are stored using two complement representation. Each sign variant can store numbers from negative 2 to the power of n minus 1 to 2 to the n to the power of n minus 1 inclusive. You know what I mean. You're reading what I'm reading. Okay. Where n is the number of bits that the variant uses, so that I8 can store numbers from negative 2 to the power of 7 to 2 to the power of 7 minus 1, which equals negative 128 to 127. Unsigned variants can store numbers from 0 to 2 to the power of n minus 1, so that U8 can store numbers from 0 to 2 to the power of 8 minus 1, which equals 0 to 255. If you're in networking, you would know. You should know that. I was in networking. And still, I'm really bad with numbers, okay? I'm really bad with numbers. Subnetting, not my strong suit. Not my strong suit. But you know what? If I have like a couple of days to remember how to do it, I can subnet. I can subnet in my head, okay? When I had to do a test on it, yes. Okay, additionally, the I size and U size types depends on the architecture of the computer your program is running on. So 64-bit is if you're working on a 64-bit architecture, and 32-bit is if you're working on a 32-bit architecture. Most laptops, machines, desktops use 64-bit. So unless it specifies that it's going to be a 32-bit, I would assume it's a 64-bit. You can write integer literals in any of the forms shown in table 3-2. Note that the number literals that can be multiple numeric types allow a type suffix, such as 57U8, to designate that type. Number literals can use a underscore as a visual separator to make that number easier to read, such as 1_000, which will have the same value as if you specified 1,000. These are the different types, so decimal types, hexadecimal. If you don't know what hexadecimal is, you probably don't need it. Octal, I don't really know what octal is. This is binary. That's what we would use in networking. And then bytes is like 8 bits. So how do you know which type of integer to use? If you're unsure, Rust defaults are generally good places to start. Integer types default in I32. That's why I'd say just use an I32. The primary situation in which you'd use I size or U size is indexing some sort of collection. Okay. Let's say you have a variable of type U8 that can hold values between 0 and 255. If you try to change the value to a value outside that range, such as 256, integer overflow will occur, which can result in one of two behaviors. When you're compiling in a debug mode, Rust includes checks for integer overflow that cause your program to panic at runtime if its behavior occurs. Rust uses the term panicking when a program exits with an error, and we'll discuss panics in more depth in Unrecoverable Errors Panic section in Chapter 9. When you're compiling in release mode with the -- release flag, Rust does not include checks for integer overflow that causes panics. Instead, if overflow occurs, Rust performs tooth complement wrapping. In short, values greater than the maximum value that is held can hold wrap around to the minimum of the values that the type can hold. Alright. In the case of a U8, the value 256 becomes 0. The value 257 becomes 1, and so on. The program won't panic, but the variable will have a value that probably isn't what you're expecting to have. Okay. Relying on integer overflow wrapping behavior is considered an error. Essentially, check your code before you release it, okay? To explicitly handle the possibilities of overflow, you can use these families of methods provided by the standard library for primitive numeric types. Wrap all the mods, wrapping such as wrapping _add, return none if there's an overflow with check methods, return the value of the boolean indicating whether there's an overflow with overflowing star methods, and then saturate at the minimum, the values minimum or maximum values with the saturating methods. I've never tried any of those, but maybe they will come in handy in the future. You never know. Floating point types. Rust also has two primitive types for floating point numbers, which are numbers with decimal points. Rust floating point types are F32 and F64, which are 32 bits and 64 bits in size, respectively. The default type of F64, because of modern CPUs, it's roughly the same speed as F32, but is capable of more precision. All floating types are signed. Yeah, I guess that would make sense that they're all signed, because you would have to only represent it with an F. Okay. Floating points are just decimals, essentially. It's the same thing as an integer, but it's just a decimal. And just specify if you have a decimal point in your code, you have to put a floating point number. You can't put an integer. It's just not going to work. It's not going to compile correctly. Numeric operations. Rust supports the basic mathematic operations you'd expect for all of the number types. Addition, subtraction, multiplication, division, and remainder, which is also, I think, called mod. Integer division truncates towards 0 to the nearest integer. The following code shows how to use a numeric operation with the let statement. This is basic math, okay? You don't know how to add and subtract and multiply and divide. There's also another one called, I think this is also called mod. And essentially you know that there's gonna be a remainder. So, and it just shows that remainder. So that's the only one that's a little bit more complicated, but other than that, this is easy stuff. This is easy stuff. Okay, the Boolean type. This is true or false. In most other programming languages, a Boolean type in Rust has two possibilities, which is true or false. Booleans are 1 byte in size, and the Boolean type in Rust is specified with the bool type. So when you're going to type them, here is a good example, you're going to type it, you put bool equals false. It's explicit. The main way to use Boolean values is through conditionals, such as an if expression. We'll cover how if expressions work in Rust with flow control. Character type. Okay, so Rust char type is language's most primitive alphabetic type. There are some examples of declaring char values. Note that we specify char literals with single quotation marks as opposed to string literals. That is a very good distinction. Do not put just one letter, one character, and have double quotations. It will not compile correctly. Rust char type is 4 bytes in size and represents a Unicode scalar value. which means it can represent a lot more than just ASCII, which is alphabet. Pretty sure ASCII has a little bit more than alphabet. Yeah, it includes accented letters, Chinese, Japanese, and Korean characters, emojis, and zero-width spaces are all valid char values in Rust. So Unicode Scholar values range from U plus 000 to U plus D7FF and U plus E000 to U10FFF inclusive. However, I don't know how big those numbers are. I'm pretty sure this is hex code. So I have no idea. You can go and look that up. However, character isn't really a concept in Unicode. So your human intuition for what a character is may not match up with what a char is in Rust. We'll discuss this in storing UTF-8 encoded strings. That's in chapter 8. Compound types. Compound types can group multiple values into one type. Rust is two primitive compound types, tuples and arrays. The tuple type. The tuple type is a general way of grouping together a number of values with a variety of types in one compound type. Tuples have a fixed length. Once declared, they cannot grow or shrink in size. We create a tuple by writing a comma-separated list of values inside parentheses. Each position in the tuple has a type. And the types of different values in the tuple don't have to be the same. We have added additional type annotations in this example. So I know that we have tuples and we have arrays. Arrays, I think, are the same types. You cannot have multiple different types with tuples. You can have different types. So here we go typing this tup, let tup, and we're going to have an I32 of F64, and we're going to have a U8. So remember, I means integer, 32 means 32-bit, F is float, or that would be decimal, and that's a 64-bit, and then we have an unsigned integer, which is an 8-bit, and we have it here. Make sure that you put them in order. Don't be messing up the order. When you type it over here, it needs to be in order over here. So the variable tup binds the entire tuple because a tuple is considered a single compound element. To get the individual values of the tuple, we can use a pattern matching the destructure to destructure a tuple value like this. So this is a little bit more in depth. This is how you destructure this value. What you're doing is that you can actually pinpoint which specific value you want. So right here we have let tup equal 500, 6.4, and 1. And remember, we are always starting at 0. That's our first number. So it's going to be 0, 1, 2. Right now we have a let this destructure, which is x, y, and z, equal tup. And we're going to print line the value of y, which is 1. If you want, you can also, actually, let me show you over here. Sometimes I get ahead of myself and I don't read ahead. So this program creates the tuple and binds it to the variable tup, like we said, and then uses a pattern with let to take tup and turn it into 3 separate variables, which is x, y, and z. So we're destructuring. This is called destructuring because it breaks down the single tuple into 3 parts, and finally, the program prints the value of y, which is 6.4. Now, we can also access the tuple element directly by using this period. And this is what I'm about to say, followed by the index of the value we want to access. For example, this is our function, we have let x equal this type, so I32, F64, U8, and then all three of these, 500, 6.4, 1. Now we have let 500 equal x, and then this little dot right here is indexing the I32, which is 500. I hope this makes sense, because we're starting from 0, remember. So let 6 underscore point underscore 4 equal x dot 1. So that's going to be the next one, right? Our F64, which is associated with our 6.4. Last one is let 1 equal x times x point 2. And our last one is the U8, which is associated with 1. I hope that makes a little bit more sense. So you're indexing which destructured portion you want to utilize. Okay. This program creates the tuple X and then accesses each element of the tuple but with their respective indices. Okay. As most programming languages, the first index in the tuple is 0. It will always be 0. Don't put 1. That'll be the second one. The tuple without any values has a special name, unit. This value is a corresponding type, and its corresponding type are both written with parentheses and represent the empty value or empty return value. Expressions implicitly return the unit value if they don't return any value, if they don't return any other value. Sorry. Sometimes I'll be reading and I don't be reading the right things. Okay? I just be reading what I think it says. That's my brain interpreting instead of reading. Alright, the array type, we did talk about this before when I was talking about tuples. This is the same thing as a tuple, but you cannot have multiple different types in this one. Okay, another way to have a collection of multiple values is with an array. Unlike a tuple, every element of the array must be the same type. Unlike arrays in other languages, arrays in Rust have to be a fixed length. Okay, we write the values in the array as a comma separated list in square brackets. Arrays are useful when you want your data allocated on a stack, the same as the other types we have seen so far, rather than the heap. And we're going to be talking about stacks and heaps when we're talking about ownerships, and I think that's going to be chapter 4. Chapter 4 is talking about ownership in Rust, and that one is going to be a little bit more complex. I'm going to have to read that ahead of time because I can't, well, I've read it, but some concepts are a little bit harder to explain, and sometimes when you're reading something and you don't, you're like, what the heck am I reading? It's one of those chapters, okay? So I'll try and make that chapter as easy and digestible as possible, okay? I'm getting hungry. Let me see, how long is this video? We're already at 48 minutes. I just want to see. So we have a couple more left. We might be doing functions, comments, and control. Let me see how. We'll see how long the functions one is. If it's too long, then we're going to end the stream here, and then we're going to start with part 2 tomorrow. Okay. Okay. So arrays are useful when you want your data allocated on the stack, same as other types we've seen so far, rather than the heap. We'll discuss the stack and the heap more in depth in chapter 4, or when you want to ensure that you always have a fixed number of elements. An array isn't as flexible as a vector type, though. A vector is a similar collection type provided by the standard library that is allowed to grow and shrink in size because of the contents that live on the heap. If you're unsure whether you use an array or a vector, chances are you should use vector. Now, Chapter 8 discusses vectors in more detail. I don't really use arrays that much. Vectors are usually the go-to. However, arrays are more useful when you know the number of elements and will not need to change it. For example, if you were using the names of the month in a program, you should probably use an array rather than a vector because you know it only contains 12 elements. Yeah. Unless... No, there's no unless. It only contains 12 elements. I'm hungry. You write an array's type using square brackets with the type of each element, a semicolon, and then the number of elements in the array, like so. Let A, colon, and then you type it, I32, colon, not colon, semicolon, 5, equals 1, 2, 3, 4, 5. There's an I32 is the type of each element, and after semicolon, that's a 5 indicating the array's content. So there's only five numbers within my array. It's a little bit different than tuple. You're not typing everything because everything should be the same type. You don't have different types in an array. You can also initialize an array to contain the same value for each element by specifying the initial value followed by a semicolon, and then the length of the array in square brackets as shown here. Let A equal 3, and then colon 5. So you have the number 3, which will be in the array 5 times. So the array A will contain 5 elements that will all be the set value of 3 initially. This is the same writing as let A equal 3, 3, 3, 3, 3, 3, but in a more concise way. So it's just shorthand. Array element access. An array is a single chunk of memory of a known fixed size that can be allocated on the stack. You can access elements of the array by indexing like this. Function main, let A equal 1, 2, 3, 4, 5, let first equal A, and then you put it in regular brackets. That's how you index it. So you're taking first, and remember we start at 0, it will be 1. And then, here, let's run it. Second, oh, it doesn't print it. You haven't printed it. It's not printed. It's okay, whatever. You understand what I'm saying. So 0 is going to be 1, 1 is going to be 2 in this instance. In this example, the variable first will get the value of 1 because the value at the index is 0 in the array, and the variable second is going to have the value of 2 from the index 1. Invalid array element access. Let's see what happens when you try to access an element in the array that is past the end of the array. Say you run this code similar to the guessing game in Chapter 2 to get an array index from the user. Alright, so here's our array. Let A equal 1, 2, 3, 4, 5. Now please enter an array index. We have our string that we want to input in our terminal. So this is for the user. Index is going to hold whatever the user input is. Now we're going to do our standard input. We're going to read our line, and if the result is an error, we're going to have failed to read line. Then we're going to let index type this usize. Remember we were talking about usize is only used for specific collections of information. This is when we use usize in arrays, in tuples, in vectors. We haven't got to vectors yet, but you understand. We're going to trim all the white space. We're going to change it to a number integer because right now it's a string. And then expect is going to be our default result error. Okay, and index entered is not a number. Yep. Let element equal a index. So we're choosing, what's A? Oh, A is here. A is our array, remember? So we're going to be utilizing A, which is our index, and we're seeing if this is actually if our user input has the correct index. Okay, and then print value, the value of the element at the index, and then we're holding that integer, that variable index, and then this is the element, which is what the user has inputted. Okay. The code compiles successfully if you run this code using cargo run and enter 0, 1, 2, 3, 4. The program will print out the corresponding value of the index in the array. If you instead enter a number past the end of the array, such as 10, you'll see an output like this. Okay, remember when we were in the guessing game? Let me see if I can bring it up. Remember when we were in this guessing game? Blah, 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 guessing game. Well, it's up here. And we put this ordering, too small, too big, greater, whatever. Okay, oh, no, here we go. We put this here. This let guess U32 equal match, and we're matching on a result. If the number is correct, or if I put a number and displayed it over a specific amount, it will error out. It will error out. So we have different places in our code that checks for these specific things. We didn't put this, or they didn't implement this within their code. And let's see what they do. Let's see what they do. I don't think they really do anything. What is this? Sorry. Sometimes it's hard for me to like read ahead when I'm explaining something. But essentially you want to put more checks in. If somebody inputs a letter, or somebody puts in the number 10 and you only have that specific array, you want to prompt the user or have that check to be like, incorrect, please try again. Or so it doesn't panic when it has that that new input that it's never gotten. So some people have a slip a finger and put a space by accident, or put another number, or things can happen. So you just want to put that check in there. The program resulted in a runtime error at the point of using an invalid value in the indexing operation. The program exited with an error message and did not execute the final print line. Okay. When you attempted to access an element using indexing, Rust will check that the index you specified is less than the array length. If the index is greater than or equal to the length, Rust will panic. This check has happened at runtime, especially in this case, because the compiler can't possibly know what value a user will enter when they run the code later. This is an example of Rust memory-safe principles in action in many low-level languages, such as Rust. This kind of check is not done. And when you provide an incorrect, is Rust a low-level language? I think it is a higher level language, but I'm not positive. Invalid memory can be accessed. Rust protects you against this kind of error by immediately exiting instead of allowing the memory access and continuing. In Chapter 9, we will discuss more of Rust error handling and how you can write readable safe code that neither panics nor allows invalid memory access. Okay, I do want to know, is Rust a low-level language? Rust is considered a high-level language due to its abstractions and features that simplify programming tasks. Okay. However, it also contains low-level capabilities and versatile languages. Okay, so it is technically a high-level language. I thought it was a low-level language, but maybe it isn't. Okay, let's look at the functions. Functions is long. It's going to be a little bit longer than I anticipated this video to be. This actually is a longer chapter. Some of these chapters only have 3. This one has a longer one. But for longer chapters, I like to break it up so we don't have to be on this live for so long. It's just a lot, okay? A lot of reading. Yeah. So we're kind of ending this live right now. I just want to say, practice, 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 okay? Rust is a very, I wouldn't say difficult language, but it is a very big learning curve. Even when you're learning these like really basic concepts and you've had a little bit of basic understanding of what coding is and how to program, it's still good to try new new little projects that have to do with this. A really good place. Was it? I think it's Rust to. I think it's like Rust to Mastery. I will try and find the exact video, but it's really good. Very good concepts. I would have to look through my folder, and you guys don't want to see how messy it is in there. In my File Explorer. So I'll try and find some of the basic level understanding of how to use these concepts once we go through it. And maybe I will do a small little course on going through the Rust to Mastery, which is, I think it's 20 examples. They also have a Rust example, Rust by example. I think that's what it's called. Let's look it up. Rust by example. They also have Rustlings, which is on your terminal. You can download it and do like these very basic. I think I've tried it one time. It's just very basic. You're fixing mistakes and the errors so that it can compile. It's really good for when you're learning syntax, things like that. Learning how to do functions, types, expressions, all that fun stuff. So here we have like hello world. Right now we're on signed integers. So look at this. It goes with the book, the Rust book. So you get to see all the signed and unsigned integers, floats chart, bool, true or false, and then here we go. It just gives you, let's run this code. Yeah. So it just gives you really good examples. Oh, sorry, you can't see. There we go. Primitives, scalar types, signed and unsigned. Here we go. Yeah. So really good examples there. That is Rust by example. It is on the same Rustling site that you can find the Rust book. And it's just going to go chapter by chapter, so I might just like put this up at the end of each chapter so you can get a good look of what we just did. It's a kind of a summary of what we just learned. Let's see. Anything else? I'm thinking about something. It's on the tip of my tongue and I can't remember what it was. Maybe I'll start putting some bullet points so that I can actually remember what I want to talk about. Anyway, this is the end of the video. I hope you enjoyed it. stay tuned for part 2 of chapter 3, and that will be happening tomorrow, hopefully at 1 p.m. I will try and do Tuesday through Friday at 1 p.m. every day, Eastern Standard Time. So I hope to see you there. Bye.